Hello and welcome to another one of D's ADD videos. Today we're going to be discussing substitution and elimination reactions. When people are looking at substitution and elimination reactions, they focus so much on the details they get lost and they fail to see the big picture. I feel like if you take a step back and see the big picture, the individual problems become a lot easier. The substitution reaction, what we're going to have is an electron-rich species. Actually, both we're going to have electron-rich species, but it depends what they do. If they attack an electron-poor carbon, an electrophile, and replaces a leaving group, then it's a nucleophile. So here we have a carbon and a halogen. This is alkyl halide. We discussed how to make these with free radicals in the previous chapter. Now, these guys are going to be attracted, these electrons, to this carbon, because this carbon is bonded to a halogen. And the halogen has a high electronegativity, so it withdraws the electrons, making this partially negative. This is partially positive. You get a dipole, and this is electrophilic, likes electrons. Nucleophiles got electrons, so it comes and binds, and either in a two-step process or a one-step process, we end up replacing that halogen leaving group with a nucleophile. What makes a good leaving group? It has to be electron withdrawing. It has to be stable when it leaves as an ion. Elimination reaction is a little different. Our electron-rich compound could be the same exact compound as we had over here, okay? But instead of attacking this electron-poor carbon, what's going to happen is we're going to attack a hydrogen adjacent to it, all right? E2 has to be anticoplanar. We'll discuss that later, but E1 can be this one here. And we end up basically having the base come in, attack the hydrogen, leave the electrons behind, and form a double bond. They fill the p orbital and form a pi bond. You get an alkene, all right? You can further make distinctions between substitution and elimination depending on one or two. So group one, for instance, you're going to be looking for weak to moderate attackers, alcohols, okay? It's a two-step reaction. First step is we're going to form what's called a carbocation. If you remember discussing these are the ones that have the MTP orbital, they're sp3 hybridized, and basically have a plus charge, 3-2-1 stability. Then we're going to either have elimination if we attack the hydrogen with our electron-rich species, or if it's attacking the electrophilic carbon here, then it's a nucleophile, and it's a substitution reaction. So the one reactions are solvolysis reactions. What does it mean to be a solvolysis reaction? It means that the solvent is what's doing all of the work. And we place a solute in the solvent, right? And the solute usually is far smaller in concentration than the solvent, and the concentration is so drastic that it's irrelevant. Solvent's concentration is irrelevant. Just the solute being the alkyl halide. So the kinetics as a result is just based on the concentration of the alkyl halide we're given. Hence the one reactions, E1, SN1. We have a strong attacker, like an alkoxide ion, all right? You might see an alcohol below it, but if you see this with an Na or something like that, then we know that it's a two reaction. And these are one-step reactions, unlike the one reactions, a little confusion. The one reactions are two-step, the two reactions are one-step. Here, we're going to form a transition state. So in the two reactions, the moment this thing binds here, this starts breaking. You form a transition state, and the moment that bond's formed, this one's broken. It's a one-step reaction, also known as a concerted reaction. Then we get our elimination or substitution. This is not a solvolysis reaction, the two reactions aren't. So you'll have the nucleophile or base, whatever it is, and the alkyl halide, but you'll also have a solvent, all right? So the nucleophile base concentration and the electrophile concentrations are going to be important here. Solvents are going to play an important role, all right? Make sure you check out the handout for which solvents are best. All right, so let's focus specifically on SN2 reactions. We're going to have a strong nucleophile, an electron-rich species, attacking an electron-poor carbon. Let's see that in action. So here we have an alkyl halide. We discussed creating these with free radicals. And this halogen here has the electron withdrawing capabilities. It's electronegative in this covalent bond, two nonmetals. And we get what's called a dipole. The carbon's partially positive, doesn't want the electrons as much as the halogen does, which becomes partially negative. So you get a dipole moment. And this carbon then becomes electrophilic. It likes electrons. So nucleophiles have electrons. So what happens now is those electrons come and attack the carbon. Now, if you remember from the big picture, this is a considered reaction, so it's going to form a transition state. The moment this nucleophile bond starts forming, this one starts breaking. So it forms a transition state. On your energy diagram, it's the highest point. And then what happens is the nucleophile takes the place of the leaving group. All right, the halogen becomes a leaving group. We already discussed the three things that make a good leaving group. It's electron withdrawing, so it can make this dipole. It's also going to be stable when it leaves. It's not a strong base. And finally, it's polarizable, so it can form the stable transition state. So the attackers, these nucleophiles, if they want to come in and actually get past these hydrogens, electron clouds, they can't be bulky, and they need to have plenty of electrons. Here are some common nucleophiles you'll find in SN2 reactions. Methoxide ion or ethoxide, not too big and bulky. Now, you will see the alcohol, but the alcohol is a solvent, all right? But if you see this CH3O minus, that's the key right there. That's a strong nucleophile. It's a two reaction. Here we have the iodide ion. It's so big, its electron density overlaps well with electrophilic carbon. Hydroxide ion is very strong. So just keep an eye out for any of these. There are many more. The alkyl halide cannot be hindered, all right? So whenever we're doing these, you'll see a primary, okay? Notice this was primary, or just a methyl halide. So if this was another hydrogen. Sometimes you might see a secondary, one of these two hydrogens replaced with a methyl group, but you'll never see a tertiary, okay? It's called steric hindrance. The nucleophile can't come in and bind if there's too many methyl groups here. Now, there's a nice picture in your book that depicts this much better than I could. Make sure you check it out and go over the concept of steric hindrance. So if there's stereochemistry in your starting material, so if it's R or S, and we undergo SN2 reaction, it'll be the opposite by the time we get done with the reaction. So polar protic solvents are ideal for alkyl halides and nucleophiles solubility. So they tend to be more soluble in polar and protic solvent. Anions tend to prefer polar aprotic solvents because they have a strong dipole moment, and that enhances their solubility. This is a two reaction, so the kinetics is dependent on the alkyl halide as well as the nucleophile that's attacking. Both of these are important. In one reaction, it's just the alkyl halide is important. That's basically it for SN2 reactions. I hope you now have enough confidence to try a few. Just know that it'll always come in the backside. Neither of these can be bulky. Polar aprotic are great for anions. Polar protic are good for the other ones. All right, so practice, practice, practice as always. Thanks for watching. Check out the example videos. Have a